Hi, and welcome to our part 3 of our writing ionic equations for those variety of reactions. And the ones we're looking at today is the amphiprotism. So as we've talked about already a couple of times before, water has the ability to act as an acid or a base, depending on what it's reacting with. If it's reacting with something that is more acidic than it will obviously then act as a base and vice versa. So what does this mean, amphiprotism? It's just that some substances can donate a proton or other substances can accept them. So that way they can act as both an acid and a base. So here we have some common amphiprotic substances listed here. If you have a look down the center component, we've got water, we've got the hydrogen carbonate, our hydrogen phosphate, and so forth here. When this one gains a proton, it will form the H3O+, but if it loses it, it can form the OH-. If we look at this one here, it's H2PO4, so it can actually still gain a proton and become phosphoric acid there, or lose one, and it is still in the acid form over here, but it has lost its proton. So there's a couple of different terms that we need to look at. We have our monoprotic acids, diprotic and triprotic acids. So with our monoprotic acids, they are the ones that you've dealt a lot with so far. We've got our HCl, HF, HNO3. So they only have one proton that they can lose. But we have another one there, a little bit of a different case, which is our ethanoic acid. So if we look at the formula CH3COOH, we can see that it's actually got 4 hydrogens. So why is it that it's considered a monoprotic acid? And the reason for that is its structural formula. And it has a CH3 and then the COOH bond, and that's that acidic proton there. So that's the only H here that can be donated in this one. And that's because, again, of this polar OH bond. We then have our polyprotic acids. So polyprotic acids are those that have more than one proton per molecule that can be donated. So as I said before, they can be our diprotic or our triprotic. So the number each molecule can donate will be dependent again on its structure. Now, if it does have more than one proton to donate, it doesn't do it all just in one step, but in a series of steps. So if we look at this one, our diprotic acid, so for example H2SO4, H2CO3, they have got 2 hydrogens there, so they have 2 hydrogens that they can donate. But it doesn't do this just in one step. So in our first step we have our H2SO4 reacting in our water or dissociating in our water, and it's forming our HSO4- and our H3O+. That one tends to go to completion. However, the second one does not totally ionize. And we've got our HSO4 again in water, and it's forming the SO4 ion, and again an H3O+. But as I said before, only a small portion of these ones will react further. And our last one is our triprotic acids, and they, as per the name suggests, has 3 protons to give away. So an example of that is our H3PO4 and boric acid H3BO3. So again, it dissociates in 3 stages. In the first stage, it's losing 1 proton, the second, the next, and the third stage till there are no more H ions left in that acid, and it's completely lost all of its hydrogen ions. We've had a go at some of those in class. I'll give you a worksheet as well. We'll just have a bit of a practice just to make sure that we are all good on those ones. See you soon.